Days, and it's good to see all of you here. It is my pleasure to welcome Vivienne Sze, the third of our keynote speakers, and introduce her. Vivienne is a professor of electrical engineering and computer science at MIT. She did her undergraduate at Toronto and her master's and PhD also at MIT. Her work is essentially in the space of computing systems to enable an energy-efficient machine learning, computer vision, video compression. And she does this through co-design. And so she's going to be talking a lot about co-design of hardware and algorithms. And the application spaces include autonomous navigation, digital health, Internet of Things. And for her work in video compression as part of the joint collaborative team on video coding, she's actually received a Primetime Engineering Emmy Award. And I think that leads to also discussing some of that co-design. She's also received plenty of Best Paper Awards in our community and also Young Faculty Awards. And I look forward to hearing about her talk.
Okay, I guess we can get started. So thank you, Sandhya and Rajiv, for inviting me to give this talk. It's really wonderful to be here. I actually want to connect today's talk with the great panel that Carol hosted yesterday, talking about efficient computing and the importance of it for sustainability. Some of the key themes that were highlighted in that panel include things like co-design, the need to work together, modeling, and tools. And I hope in today's talk I'll be able to cover that. In particular, I just want to express that, in the past, for my own PhD, I worked, from an interdisciplinary area looking at the intersection of circuits and video compression. And actually, I came to this community through collaborations with Joel Emmer. And so I think it's really important to, leverage co-design and collaboration to enable high-impact research. And so one of my goals for today's talk is to, through examples in my own research, try to illustrate ways in which we can do co-design, and hopefully it'll inspire many of you to think about how you might have opportunities to do co-design in your work as well, and hopefully this can extend and increase the impact of a lot of the exciting research that's going on in this computer architecture community. Okay, so let's get started, and I just want to highlight that a lot of the work that's being presented today is in collaboration with various folks, and I'll highlight that on the way. Okay, so I think we've already established this, especially from the panel yesterday, that obviously there's a significant growth in terms of the amount of energy that's going towards computing. One of the biggest drivers is in the data centers. We know that already back in 2022, it already accounted for 3% of the US global electricity, and it continues to grow very rapidly. The one thing I also want to highlight is not just in the data centers, but obviously we deploy computing on a wide range of applications, and there's a lot of exciting applications, like, for example, autonomous vehicles. So in Carol's paper, she had highlighted back in MLSys 2021 that, if you look at the number of inferences in Facebook's data centers, it's on the order of trillions. Well, if you take a look at autonomous vehicles as an example, one of the key things that you have to do in an autonomous vehicle is to understand your surroundings. So as a result, you often have many cameras, and you have to run a lot of processing on the video feeds that come in to understand what's in the content, so often many neural networks. So let's say if you set up the problem with 10 cameras, you need to run 10 neural networks on these cameras at 60 hertz. For just one autonomous vehicle, you would be running around 22 million inferences per hour driven. And then if you just scale this up, only to, let's say, 1 million autonomous vehicles, and this, just keep in mind, this is 0.1%, or less than 0.1% of the number of vehicles worldwide, that would already give you around 22 trillion inferences per hour driven. So this is not to say that we shouldn't explore autonomous vehicles. Obviously, there's a lot of promise in terms of reducing car accidents and so on, but I think what's important here is to realize that even in exciting emerging applications, there's a huge amount of compute that's needed, and we should think of ways to address it. The other thing that we care a lot within my own group, too, is looking at smaller devices that are battery operated. And so as a result, the amount of energy that you have that's available is limited by the size, weight, and cost of the device. Furthermore, often these devices, whether it be a phone or a small robot, has very limited ways in which to remove the heat. So often the power consumption that's allowed often is very low, below a watt. Okay, so these are the restrictions that we have, and these are the challenges that we face. So as I mentioned in our group, the key way that we go about doing this is through cross-layer co-design. And that'll be the theme of today's keynote or talk. So we're going to first start out with architectures. You guys are all obviously familiar with that. And looking at designing architectures with the circuits and possibly the devices as well. And so the first kind of section of today's talk will be looking at the co-design across the hardware stack and how can we bridge these areas and enable co-design. The second thing that we'll look at, so with each of these kind of extend further out of your comfort zone, which we'll be looking at algorithm design and how we can do algorithm design with the hardware. So we'll be looking at the co-design of algorithms and hardware together. And then finally, it's also really important to think about the overall system. Computing is not the only thing in the system, and in the context of our particular interests, we're looking at autonomy and robotics. So when we talk about the system, we're looking at the computing and how it interacts with things like sensing and actuation, which is the energy to move around the robot. And so the last section of this talk is going to cover the co-design across the system itself. Okay, so these are the three areas. And so we're going to start with the most comfortable, which is co-design across hardware, and then we're going to extend your comfort zone to algorithms and then systems. Okay? So let's go with the hardware stack. And so in this work, I'm going to feature a lot of the work of these collaborators. A lot of them are students that I co-advise with Joel and our collaborators at NVIDIA. Okay, so you might recognize the faces. Okay, so the first thing, again, I came here from a circuits design community, and what I learned from this community and working with Joel is that, one of the key strategies that you guys take is to do modeling to enable design space exploration. And so just very briefly, in terms of the work that we've done recently on this, is looking at, of course, modeling of the space for designing sparse tensor accelerators. This is obviously a very important type of workload, and there's whole sessions on this at this conference. So some work that we did called sparse loop. And then with this actual modeling tool, we design accelerators. So for example, we had this work highlight that was presented at Micro last year, looking at kind of balancing flexibility and efficiency. So how do you support a wide range of sparsity patterns, but keep the cost of the hardware simple? And so the key insight here is that we used basically exploited hierarchy, so that your building blocks are cheap, but when you put them together, you can express a wide range of sparsity patterns. Another accelerator that we looked at was trying to address the issue of trying to figure out what is the best tile size to use. So for those of you who know, generally speaking, the larger the tile size you have, the better. But one of the challenges for this in the sparse tensor workloads is that the number of non-zeros, or the occupancy, is not really known across the tensor. It varies a lot. So basically, if you design or if you select the tile size in such a way that you always guarantee that the number of non-zeros or the occupancy will fit into the buffer, you'll have cases where the buffer will be underutilized, because obviously there'll be less worse cases. And so inspired by the idea of airplanes and overbooking, what we would like to do is have the hardware be able to handle the case where the tile does not actually fit into the buffer. And so if there's some bumped data, or in the analogy of the airline, some bumped passengers, you have a mechanism to handle that. But as a result, you can have a larger tile size, right? And this work is, so basically there's two components of this work. There's tailors, which is like a hardware mechanism that allows you to handle the bumped data, and then there's Swift tiles that allows you to figure out what the tile size is. And if you're interested in learning more about this, I encourage you to take a look at both of the papers. In particular, I hope you are enchanted by the name of this paper. Okay, so let's turn towards one of the bigger challenges that we face. Again, this should be no surprise to this audience that obviously data movement is really what dominates energy consumption, and so there should be a lot of focus in terms of the architecture and the rest of the hardware stack to address data movement. And so one of the key strategies that people take to do this is doing compute in memory, and actually Ritu received an award yesterday for all her great work in this space. So I'll just briefly summarize kind of what is the approach in this space and why it's important. So the idea is as follows. In conventional hardware, you basically, we're going to use an example of deep neural nets. So you have the inputs and the weights. Those are read from memory. You do the computation from them, and then you store the output also in memory. The idea behind compute in memory is to say that, well, data movement's expensive. Can we avoid moving some of the data, in particular the weights? So instead, can we bring the compute into the memory that's storing the weights? So you just have the data movement of the inputs, and then you have the resulting outputs that come out. Okay, so this is great, and actually this is a very active area of research across the entire stack, right? So if you look at circuits conferences, so ISCA'24, VLSI, they have whole sessions dedicated to this. At IEDM, looking more at the devices, they again have sessions and workshops all dedicated to this. And even here at ISCA, we have obviously a lot of interest in this space as well. So I think the key thing is, can we, rather than have a lot of researchers work in isolation in their different communities, can we bring these folks together so they can collaborate and work on it, and we can get the best of all these different approaches and have a very effective and high impact solution, because this is a very important problem. So I'll discuss one strategy that we've taken in our group to try and help enable this. So in particular, let me just again briefly review how you would map a workload, for example, in DNNs to a compute memory accelerator. So one of the key kind of building blocks in DNNs would be a matrix vector multiplication. So you have like a vector of inputs, you have the weights, which are matrix, and then you have the output. So let's say you are storing the weights, which are matrix, in the memory. So what you would like to do is then you would then to send the inputs to this array and do some form of computation in the memory device itself. And then, as I mentioned, then the output just streams out of the memory. And again, since you've done some computation within the memory, the output bandwidth is also reduced. This is great. In the wide range of research, the computation can happen in either the digital domain or the analog domain. If it happens in the analog domain, then you might need some D to A to D converters. And so that's the general setup. And so this is actually a large design space. So for example, there's a lot of different choices that you might make for the devices themselves, right? So you could use memoristic devices, SRAM, DRAM, and even in the context of these devices, there's a lot of research in coming up with better memristors, for example, different ways to use the DRAM and SRAM and so on. There's also the circuits that you might have, so the A to D, the D to A's. I think Ritu also mentioned a lot of the innovations also in the peripheral circuits, so there's a lot of opportunity for innovation at the circuit level, and that's what a lot of these publications at ISSCC cover. And then, of course, here we're very familiar with the architecture, which is basically how do you assemble these components together, how are they actually connected, what are the size and the size of the array, the size of the memories, and so on. You might also want to think about what is the workload. So in this context, it would be, what are the size of the matrices, the size of the vectors, and so on. And then, of course, there's a huge amount of work in this community looking at how do you map then this workload onto the architecture itself. So I'd say that, probably in this community, we're most familiar with the workload mapping and architecture aspect of the design space exploration. What we would like to expose, and in terms of a kind of a deeper flexibility and ability, is the circuits and devices, and how the circuits and device design choices might impact some choices up at the mapping, architecture, and workload. Okay? And so in order to do this, to cover this very kind of deep, wide design space, we need to have some modeling tool to actually support this. And so we've developed a tool called KIM Loop, or KIM stands for Computer Memory Loop. So this is some work that was actually published at ISCA'24 maybe 2 weeks ago. So let me walk through it very briefly. So it's basically based on top of time loop and Accelergy. So for those of you who have been kind of following the mapping space for these spatial arrays, I think that's a tool that has come out from our group that people have used for the mapping exploration. So it takes in the workload and the architecture. How we want to augment this is you also want to take in the circuits and the devices. You want to be able to take in a description of these values, be able to model it somehow, which I'll talk about next, and put that in and have that be accounted for during the mapping itself. So then the overall system allows you to take inputs of workload, architecture, circuits, and devices, and then the output will be energy estimate, area estimate, and the overall throughput. Okay, that's kind of the setup of it, and I'll focus on the left-hand side, which is basically the contribution of this paper and how we enable information about the circuits and devices to be actually put into the mapping framework. Right, so what are the challenges that we face in order to do this? So the first is obviously you need to have some interface that is flexible, right? Because you want to be able to basically describe a very large design space of these particular components. So just to give you an idea, if we take a look at a range of publications on computed memory from various different communities, so JSSC is the premier journal for circuits community, of course, with ISCA, Nature, and so on, VLSI. And if you look at the components that are used across these particular publications, there's a huge amount of them, right? So you need to have some flexibility in your description in order to be able to represent these. And so one of the capabilities in the tool is that you can, first of all, we built a library of these circuit and device models, and then there's a plugin that allows you to interface with the rest of the modeling tools so you can create more models as well. So you need to have this flexibility. The next thing, of course, is that you need to model the energy accurately, right? So if it's not accurate, then really who cares about the modeling tool? And as it turns out, for these particular devices, it's really critical to understand a variety of things in terms of the workload and the representation of the data and how it affects these different, the energy cost of these different devices. It'll change depending on whether or not, let's say, your memory device is a memoristic device or an SRAM. They're going to consume different amounts of energy for different types of data. And you want to capture these through the cross-stack and the cross-stack interaction. So we're able to do this within about 8% of the measure results. And just to give you kind of a high-level kind of insight in terms of how this is actually done. OK, so the idea here is as follows. So let's use memristive devices as an example. Right? So for those of you who are not familiar, memristive devices, you can basically program its conductance. And the ways they've been used for compute and memory is that typically the conductance is representative of the weight value. Right? And so basically, you have the weight value, which is the conductance. You have a voltage across it, let's say, which would be your input. And so with Ohm's law, then you get the current out. And so that's like a free multiplication. OK, so the energy cost for these particular devices, even though they're identical, these two memristive devices, but the energy that they will consume depends on the value that you write to it. So for example, on the left-hand side, if you're writing a value conductance of 3, then the energy consumption would be 3 femtojoules, versus if you're writing a value of 1, the energy consumption would be 1 femtojoule. So you want to be able to capture this data dependency. And in prior modeling tools, it often assumed that the energy was fixed. Okay, so this is a really important factor, and of course, this relationship between the workload value and the energy consumption depends a lot on the type of component that you have. So that's why it's important to reveal the type of component as well. This is how we calculate the energy. And of course, in terms of what are the values that are actually mapped onto these devices, well, there's many factors. Right? So first is like, what is the value we're actually trying to process? So what is the weight of your neural network? And then it's like, well, how do you actually represent this actual weight, right? There's many different ways you can represent the number 13 in binary. You can be unsigned, differential, XNOR, so on. And then there's the choice of often we can't fit all of these bits on one particular storage element, so you might need to slice it or break it up apart. And how do you go about doing that? That's another design choice in terms of how you partition these bits. So all of these have to be factored in before you figure out, basically what is the value that's mapped to these particular devices. So you want to be able to capture all of that. And if you can capture this kind of data value dependency of what value, how we represent them, and where we map the bits, then you can capture the energy consumption. Okay, and then of course the last thing that we care about, because the whole idea here is that after we've modeled it, we want to explore the design space, and you don't want to be waiting a very long time for the energy result. The whole goal is to try to go fast so you can have some idea about where the energy is actually going. So rather than simulating each value independently, what we try to do is exploit a statistical model. So rather than looking at each individual value, you look at the overall distribution of the values, and that actually gives you several orders of magnitude speed up compared to prior models. And so just very briefly in terms of what is the context of this work, as this Kim loop work as compared to prior works. So if you look at, for example, time loop, which it's built upon, time loop is data value independent. So that's the case where we're kind of fixed in terms of the energy per operation. And so by basically capturing the data dependency, we have the same speed, but 10x lower energy. The next comparison point would be from NeuralSim, which is more from the circuits kind of community. And there you can imagine they want to be very accurate in terms of the energy estimation, but they really look at each individual value at a time. So it's very slow. And so if you use more of a statistical distribution of your values, you are able to speed it up by an order of magnitude. Okay, so that's at the very high level, the insight in terms of how Kim loop is both fast and accurate. The other exciting thing that we found with Kim loop is actually, the whole original goal was to model compute in memory. But as it turns out, there's a lot of similarities in terms of the processing that's being done for these photonic accelerators. So for those of you who are not familiar, the idea behind photonics accelerators is as follows. Since data movement is expensive, particularly if you represent the data in terms of electricity, the idea there is that if you can represent it in terms of light, then the cost of the data movement is significantly reduced. So there's this whole body, or whole body of work and a whole research community centered around doing computing with light. And they build all these different photonic accelerators, and we want to be able to model them so they can also do design space exploration there. And the key kind of alignment between compute and memory and these photonic accelerators is that, as I mentioned, compute and memory, if you're doing it in an analog domain, you need to analog to digital converter, digital to analog. Again, in photonics, they have a similar requirement, but also in addition to that, they need electrical to optical, optical to electrical. So you can imagine how you can fold that kind of functionality together in this framework. Okay, so we've done some modeling also illustrating that we can model their accelerators using Kim-loop. And then also just to show that we're not just telling you, oh, this is one strategy within MIT ourselves. So Joel and I have been collaborating with various folks within MIT to leverage Kim-loop to do cross-the-stack design. So for example, Jesus Dalomo really focuses on new memristive devices, or these programmable resistors. And so we're using this tool to allow us to explore the impact of their particular device at a system level. Similarly, if we look at some of the work we're doing with Dirk England, he's looking at the photonic accelerators, they're computing with light, and again, we want to be able to enable them to do design space exploration and leverage a lot of the innovation we have from the architecture community to design their photonic accelerators. And what we've also found that this has been helpful to help kind of identify the right level of abstraction that we need when we talk to these folks. I mean, some of you might have tried to collaborate with folks more on the device and circuit side, and sometimes I guess from a communication standpoint, sometimes it's lower level details, but here with this actual modeling, it kind of allows us to have an interface in terms of discussing how we want to actually connect. Okay, so this is just one strategy that we've taken. Again, I want to encourage you, if you want to kind of do cross-stack design, think about how there might be opportunities to leverage a lot of the modeling and the tools that you've designed in this community to help facilitate that. Okay, so why is it not moving forward? Okay, so what are the kind of key takeaways from this section? So first is, okay, so I don't need to tell you guys, but like modeling is used widely in this community for design space exploration. And what I hope you take away from this is that you can extend potentially these modeling tools to support circuits and emerging devices. And this helps to two things: broaden the design space, enable co-design across the space, so you could basically see, oh, with these new devices, what is the impact? What is the impact at the system level or at the architecture level, and vice versa? If how I might change the architecture for different types of devices. And then also, this modeling can be used to enable collaboration across different research communities, and really hopefully increase the impact of a lot of the great work that everyone is doing, and ensure that we're all moving forward and actually solving meaningful problems with our effort at our research. Okay, so that's the hardware stack of things. So let me move on to the next section, which will be even more challenging. So now we're going to look at the co-design of algorithms and hardware. And then a lot of this work is done in collaboration with Surtesh Karaman, who's a faculty at MIT and more of a roboticist side of things, and some of our co-advised students. Before I get into the robotics thing, I want to start with something that maybe, again, this community is more familiar with. So obviously, one of the key workloads that we care about is deep neural nets, or LLMs. And this actually was brought up in the panel yesterday, too. Can we factor in some of the key hardware properties or hardware metrics in the design of these DNN workloads? And I think that's really important, as opposed to just looking at accuracy or number of ops and weights. So for example, in some of our prior work, we looked at, for instance, some of you might be familiar with the task of pruning, which is setting some of the weights to 0. Previously, kind of a straightforward method was to look at the magnitude of the weights and remove the smaller weights. But as all of you know, it's not necessarily the size of the weight that affects the energy consumption. So if there's a way to model the energy consumption of the DNN, and you prune away the weights that consume the most energy, you can actually, for the same accuracy, achieve a more energy efficient design. So the high level message here is that if there's a way that we can put energy into the objective function, we can achieve a better trade-off between energy and accuracy. Another thing, and so this is some work that we did in collaboration with Google's mobile vision team, is based on this energy-aware pruning. They were interested in seeing that if we can automate this whole process. In particular, can you put in, for example, a processor on a cell phone and automatically fit the DNN onto that given platform? Again, at the heart of this, the key idea is to keep the hardware in the loop. So you're taking hardware, or you're modeling the hardware measurements of latency and energy, and then you're optimizing with latency and energy as a metric that you're trying to balance with accuracy, as opposed to things like number of operations or number of weights, because the latency and energy is much more hardware dependent, and you're going to get, as you expect, a much more effective trade-off. Finally, another thing that we had looked at was, can we kind of rethink the design of DNNs, particularly for compute and memory? Often we have all these exciting compute and memory accelerators, but they're often evaluated on existing DNNs that are out there. And we know that kind of the trend for DNNs, at least for convolutional nets, were primarily to increase the number of layers and reduce the number of weights per layer. Okay, so that was the foregoing strategy, things like MobileNet and so on. But if you think about compute and memory, actually it works very well with very large layers, because the whole idea there is that we're trying to reduce the data movement of the weights. And in particular, often for compute and memory, you need to have a large array of these weights in order to amortize the cost of the analog to digital and digital to analog conversion. And if you have a very small layer, you're actually not fully utilizing all the quote-unquote compute or memory elements that you have in your array. So instead, it might be better to redesign these neural networks specifically for KIM. So for example, you might actually want layers that have more weights, and then you might want to have fewer layers, because actually the cost for KIM is moving the inputs and outputs through the system, and so the more layers you have, the more inputs and outputs that you have, as opposed to having these larger weights. So these are just kind of three ideas in terms of how you could potentially use hardware properties to drive the design of a DNN workload. Okay, and so I think there's a lot of active research in this space, but often it's still kind of doing things like changing the number of weights, changing the number of layers, and like the dimensions of each layer in terms of number of channels and so on. But it's not really completely changing the algorithm itself, so the design space is still kind of limited in some sense. And so what I want to do is kind of walk you through some examples in the robotics space that are not DNN related, but to give you an idea in terms of how you can completely change an algorithm to make it more hardware friendly, and go through that co-design process. So let me start by slowly try to walk you through some of the key, one of the key building blocks or key tasks in autonomous navigation, which is particularly building and storing maps of your environment. Okay, so this is actually, a high definition map is really, for some autonomous vehicle companies, is really deemed as very essential to enabling their technology, and it actually results in significant compute costs both in the data center and at the edge. Okay, and so what do you use these maps for? Well, if you can build a map of your surrounding, you can use them for things like localization, figure out where you are, navigations kind of decide where you want to go, and at the same time also do things like obstacle detection, avoid certain obstacles around. And the key thing from a compute standpoint that we need to be able to do is to build this map and also store it, while at the same time delivering, obviously, real-time performance to go, real-time in terms of speed within an energy constraint. Because even in these autonomous vehicles, these very large vehicles, you still have power constraints. It's going to affect, how long you can drive for example, in a given charge. In our own research group, too, we're also concerned with building or enabling autonomy on smaller scale robots, what we call low energy robotics, where the cost of moving or actuation is under a watt. So it's hard to kind of imagine that, but you can see examples like a blimp doesn't require that much energy to move. They have these long duration sea gliders that go under the water to kind of explore deep space and collect data. That's also, deep sea to express data, and those are also under actually a watt of actuation power. And so here you can imagine if the cost to move is so low power, you also want to ensure that your computing energy to make these things autonomous is also very low. So you have very tight constraints here as well. Okay, so let's kind of do a little tutorial in terms of, what does it mean to build a map? In particular, one of the key maps that we need to build is called the occupancy map. So what does that actually mean? So an occupancy map indicates the probability that there's going to be an obstacle in a given location. Okay, so you might first start off, let's say if you completely don't know the space, you start up by initializing the map at 0.5 for every possible location. So it's all unknown. Probability between 0 and 1, having an obstacle, 0.5, unknown. Then what you would do is you would place a robot in the map, and it would scan the surroundings, probably with like a depth sensor. So for example, if you were an autonomous vehicle, you'd use something like LiDAR. And so you can see, so I put the robot there in blue, let's say in that location, and it's going to be scanning with the red rays around. Let's say in theory you could scan all the way around. And so based on what these rays hit, it's going to reveal whether or not a certain location or a certain cell is either free, which is shown here in white, meaning that there's unoccupied, so you can walk there without crashing into anything, or occupied, which is shown in the black, which means that there's an obstacle there. Okay? So that's basically how you build this occupancy map. And an important thing to mention, though, is actually the map is probabilistic because the sensor itself also has noise. So you can never be 100% certain because of the noise of the sensor in terms of whether something is occupied or not. So rather than, in this illustration, I showed you 3 values, basically 0 for free space, 1 for occupied, and 0.5 unknown. But I want you to think about it, it's actually probabilistic. So the numbers in this occupancy map are actually continuous, right, between 0 and 1, and it depends on the noise sensor. Okay, so it's a really important part to capture that. And you can imagine you can increase the probability by, scanning the certain things multiple times. Okay, so this is just an illustration live of, a robot exploring. So I know it's not starting from unknown, but you can see it's going through the various different locations, and the red is, the robot's in blue, and the red is depicting where the depth sensors are lying, and it can reveal and open up, kind of unknown environments, right? And so as it's doing this, it needs to both build and store the map. Okay, so I hope we all understand what occupancy map is. So one of the challenges in this space, is fine. You want to build a map, and let's say you want to build a map of an unknown environment. So this is typically in the application of, let's say, search and rescue. You're dropped in a new space. Where should you actually go? You could also imagine this is like, in some sense, tourism. When you go to a new city, like Buenos Aires, you're trying to figure, where should I go to get the most amount of new information? I want to see new stuff. Okay, so you need to select the location to move to reveal the most amount of new information about that environment. Okay, that's the task. There's been a lot of research about this within the robotics community. And one of the interesting and most promising approaches is to use Shannon's mutual information, right? So the idea here is that if you can compute Shannon's mutual information, this is obviously from info theory, of your environment, you could actually indicate, which location has the most amount of new information to be gained. So if we show like a map here on the left-hand side, this robot has to decide. We compute the mutual information of this map, and it shows that, if you go kind of the top region where it's brightest, you can have the most amount of new information because then you can scan these unknown areas from that bright location versus kind of going further down and you're blocked by the walls. And so a nice thing, and what's really important in the robotics space, is they really want things to have provable guarantees. So they can guarantee, for example, that you're actually going to a location that has the best amount of new information. It's very critical there, and they're able to show back in 2014 that if you can use Shannon's MI to do that. And furthermore, it's really important, as I mentioned, that they count for the depth sensor noise, the noise of the sensor as well. They can't assume that everything is perfect, because nothing is perfect in the real world. Okay, so this is ideally the strategy that they would like to take. The problem is, right now, MI is not feasible in real time. It's actually several orders of magnitude too slow. So it's all basically thought of as some theoretical thing that would be great to have, but we can't do it because it's computationally too complex. Well, for folks like us, that's great to hear, because if I can make it, or if we can make it more computationally more efficient, we can make their dreams come true, right? So let's try and do this and close this several orders, and by several orders of magnitude, I mean like millions. Factor of millions off. Okay, so what are the different strategies that we take in order to do this? So the first is trying to change the algorithm itself. So let's again walk through this a little bit slowly. So for a given location, you might do a depth sensor, right? You might have one single ray, and the idea here is as you scan the ray across for this, basically what you would like to say is like, if I were to emit a depth sense here, how much for each of these blocks, each of these cells, how much mutual information would I be collecting? And in some sense, the idea is that, the more cells that have a probability between like near 0.5, the more unknown these locations are, the more information I will collect, right? So this is kind of estimating, how unknown are these regions. If they were all, had a probability of 0, like if you already knew that they were unoccupied, for example, why bother scanning? Why bother going to that location? So that's kind of what you're trying to collect that information from. Okay, just at a very high level, the way in which we compute this in the original paper was that they look at it at one cell at a time, like for each of these cells, how much new information can I get? But unfortunately, by doing that, it requires some numerical integration, so the complexity is n squared, n being the length of the ray, lambda z. And so some of the work that we did was try to reformulate this, and we recognized that if you compute all the cells together, you remove this numerical integration, and that has a significant impact. So I know it's kind of mathy, but just as an analogy to kind of understand what's going on, it's kind of like in the arithmetic series. If you were to add up a bunch of numbers, one at a time, right? It would have a lot of compute there. But if you know that you can compute this all at once, then you can just use the arithmetic series formula, and that's going to be much more efficient. So it's kind of the similar type of thing in terms of the strategy that we're using here. A little bit more complex, but that's the key idea. And then actually, by doing this, you actually get 3 orders of magnitude speed up, right? Which is great, right? So if you can do this type of kind of reordering of the data and reframing it, then you can actually, it's a little bit more than reordering, but you get orders of magnitude speed up, which is hard to achieve just using hardware. OK, so this is just a robot doing this FSMI compute, basically exploring this space in real time. You can see it keeps on trying to go to the very bright part, the high mutual information location. So it indeed works, but this video is being played back at 4x real time, and there's a huge compute engine on this robot. So we want to further speed it up. OK, so now let's go to the hardware side of things. OK, so now we figured out a way to make these rays compute very quickly. And in theory, that was just one kind of depth sensor. But you could imagine, you have depth sensors in many directions, and they're independent. So it should be possible to compute all of these depth sensors at the same time in parallel, which we love to hear in this community. So parallelism is possible. What is always the challenge with parallelism, other than resources? It's the memory bandwidth. Right now, we need to be able to deliver the data to all these parallel engines. And in particular, now these engines, because of that FSMI stuff, we made them super fast. So the bandwidth that we need to deliver is very high. It's not like we can slowly deliver the data. And so what's really interesting is by doing that algorithm design for FSMI, we kind of shifted the bottleneck from compute to memory. Right, so that's kind of one of these tools that we have by redesigning the algorithm. We can move the bandwidth around and figure out, or move the bottleneck around and figure out a place that hopefully hardware folks can actually address. So what can we do here? I think this is, I'll just reiterate this, but I think you guys all know this. So the power consumption of the memory will scale based on the number of ports. So typically, you want to use like a 2-port SRAM. Of course, if you just had a 2-port SRAM, you would not have a sufficient bandwidth to deliver to all these processing elements. So what do you want to do? You're going to have to go with banking, right? You have to break it up into smaller banks so that you have more ports. The challenge, of course, is that what should the banking pattern be? Because effectively, you have this kind of ray spreading problem that goes around in the entire map. So what this is illustrating is kind of the axis pattern. So you have the rays going at the different angles. So the colors are different rays. And then the number that's being illustrated here is the order in which they need to access each of these different cells. So it kind of radiates out. So you can imagine a number, the same number means during the same time step, it's accessing those regions. Okay? And so what we need to think of is how to basically bank or break up this array of data into such a way that the same number, which is like the data that's being accessed in the same time step, is not does not appear in a given bank more than 2 times, because we only have a 2-port SRAM, right? So how should we actually bank this? As it turns out, you can use diagonal banking to do this. So you can bank it diagonally. And you can see for each given color, which represents one bank, a given number or time step only appears twice, because it's a 2-port SRAM, so there's not that many stalls. Okay? Later on, we had some work that proves like a Latin square pattern does even better than this, but for this particular publication, this is what this is. And this allows us to, with specialized banking, give a 6%, increase the throughput so it's within 6% of the theoretical limit. So if you had unlimited bandwidth, the throughput of this is within 6% of that. Okay, so you don't have that many read conflicts, basically. Okay, so again, this should not be too new for this community, but we can see how we've done something from the compute side to speed it up, and then within the hardware, we can do something to handle the bandwidth to ensure that we can deliver sufficiently to these super fast cores now. But still, it's not fast enough. So we again have to return back to the compute side of things and think of another way to further reduce the amount of computation. So then we can formulate the algorithm, and the idea is as follows. Well, I don't want to just compute the mutual information in one location. I would actually like to check what is the best place in the overall map. Not just like, is this location any good? Is this location any good? If I can check all locations, then I can get information faster. So if you think about looking at different locations, location number 1, let's say it's scanning to the left. Well, in the next neighboring location, you would also be scanning to the left, and you would overlap a bit with the first one. And then you could imagine, oops, where's the animation? Is it stuck? Okay, so then there's some overlap, some reuse potential. We like to hear that word in this community. So there's some reuse that you can exploit in terms of the computation. Uh-oh. Is it so slow? Okay, let me keep on going. But anyways, you get the idea. So there's a lot of reuse around. Is it? I don't know. There's like a latency. Okay, anyways, I think it's fine. So if you did all the possible positions, there's like a lot of potential overlap that you can actually exploit. Again, this doesn't come for free. This actually came from changing the algorithm, so all of a sudden there's a lot of data reuse, or reuse in terms of computation. And so if there's a lot of reuse of computation, you can replace all of these rays with a single ray that just crosses the entire map. Okay, so again, this is very fast, but this is at the high level. The high level idea here is that you change the algorithm, so there's more opportunities for reuse, which is then great from a compute standpoint. And so you want to expand this into the entire map. Right, so if you were to do this in the entire map, basically now it's very simple in terms of how you're scanning the data and accessing the data pattern. And what does this give you? Well, actually, this speeds things up by another 2 orders of magnitude because you're reusing a lot of the data. Now, the key word I want to emphasize is that you're reusing the compute, or not the data, they're reusing the computation, but it's recursive, meaning that each location depends on the result from a previous location. And again, this kind of is actually introducing dependency, which often is a challenge. But again, we have strategies in this community to deal with that. So in particular, they are dependent, but you can actually time interleave and map multiple different rays to the same processing element, so that even though the processing element is pipeline, there's no stalls, right? This is a strategy that you guys are all familiar with. So that addresses that key issue in terms of the dependency that was introduced by reducing the number of operations. And then also in terms of the banking pattern, we also already talked about that. You can figure out a banking pattern so you can do all of these rays at the same time so there's no conflict. Again, these are strategies that you guys know very well in this community. Okay, so that's a lot, but let's summarize in terms of what is the kind of overall impact of this. So the key takeaway here is you can achieve several orders of magnitude of speed up through this co-design, right? So we first started off by changing the algorithm itself in such a way that when you compute many things together, you significantly reduce the number of computation by several orders of magnitude. Then that kind of shifted the bottleneck to a memory kind of issue, and then we applied a banking strategy, which again we know very well from the hardware community that can actually address this. Then again, you still have to reformulate the algorithm to again reuse some of the computation itself. But the challenge there is that it has some kind of recursive structure, it introduced some dependencies, and then again, from a hardware strategy, you address that with some time interleaving and your PE, and it's fine. So as a result, by doing all of this type of stuff, you actually get many, I think like 10 million orders of magnitude speed up. And what does this enable? Well, it enables us to do mutual information for the entire map in real time for the first time. And so keep in mind, this was something that the roboticists thought was not even feasible back in 2014 when they proposed it. They were like, theoretically, it would be great if this is possible, but it could never happen. But through co-design, you can actually significantly close this gap. Okay. Okay, so one other quick thing. So that was through mutual information. So that's how to build the map. Like, where should you actually go to build the map? The next question that we actually have is, how do you actually store the map? Right? So now we're starting to really deal with memory, which I think we all agree is a big challenge. And so ideally, what you would like to do, or the factors that we care about, is how compact the map is. If these maps are very huge, or they're very unwieldy to build. And a lot of the existing frameworks are very limited in terms of the compactness of the map. The other thing is, as you're building the map, how much compute is there? So how often do you have to cycle through the map to make certain decisions in terms of how to compress it? So whether you do a multi-pass approach or a single-pass approach. And then also, how much memory overhead is there that exists while you're building the map. So it's not just the size of the final map that you care about, but I mean, all of you are familiar with the fact of, how much memory are you using while you're building the map itself? So during the processing time, you also have a lot of memory bandwidth and memory storage. How big, how wieldy is that? And so we want to address these 3 challenges using what we call a Gaussian-based representation. So let me kind of explain what that looks like again. So how do you build a 3D map? Basically, you have, as I mentioned, a robot that's going around, and it's not just like a simple depth sensor. Actually, what they're actually taking is these 2D depth images. So if you've played with Connect and so on, you recognize that each of these points is indicating how far away a given object actually is. And you're going to conduct like thousands, hundreds of thousands of these, depending on how far you actually go. And so typically what people do is they stitch these all together into a 3D point cloud, right? So you have a 3D point cloud that is like full of different points. Obviously, the cost of storing this and managing this, especially as you build larger and larger maps, if you explore more spaces or if you need high definition, is very costly. And so what people have done is they've turned towards things like summarizing this or reducing this with kind of a voxel-based 3D map. So rather than in 2D you have array and 3D you have voxels. And this can give you an order of magnitude reduction. But even more effective, and this has become a popular way in the robotics field to represent it, is to use Gaussians. To represent. And the reason for this is it allows you to have a lot more flexibility in terms of your building block, right? So for example, I don't think I have do you have a pointer here? Anyways, the top region, let me go back. Okay, so you see like the top region of the map there, there's this one like uniform region. You typically have to represent that with many boxes in the voxel base, but with a Gaussian, you can just represent it with one Gaussian itself, and it can span that area. So it can be much more flexible in terms of how it's representing the building blocks within your map. And also the description of the Gaussian is pretty simple. You're just talking about what is the mean, what is the variance, and so on. Okay, so actually if you go all the way to 3D Gaussians to represent your map, you can actually reduce the size of the map by 16x, and it still achieves similar accuracy compared to these other representations. But the process of figuring out how big that Gaussian should be, how much of this neighboring information you should fuse to make this Gaussian is actually computationally complex. So you're basically trying to see, should these neighboring values belong in the same Gaussian? Should I merge them in the same Gaussian, or should I keep them separate to do this kind of adaptive type of style? And so as it turns out, though, what is an effective strategy for doing this is rather than trying to figure out the Gaussian from the point cloud, if you actually figure out the Gaussian directly from the original depth map, it's very clear which locations are associated with each other. And so you can go from this depth map to the Gaussian in a very single pass, row by row manner. Single pass means lower memory bandwidth. You don't have to access the same data over and over again. And the fact that it's row by row also means that your storage is smaller and you have smaller memory. You can keep a lot more locality doing this. And so this gives you a 50x reduction. And then, of course, you have many of these images, and you're going to merge them all together to form the whole 3D point cloud. And if you do this type of processing with the big Gaussian building blocks, as opposed to these little point clouds and merging them together, you also reduce memory overhead by 8x. So the purpose of this last part was just to really show how if the algorithm designer is aware of some of the hardware challenges, which is memory, they can really rethink in terms of how they do the design itself. Okay, so this was a lot, I know. So what is the key takeaway that I want you guys to get away from all this section? First is that there is a limit in terms of how much improvement you can achieve from hardware alone, right? So we were millions, or 7 or 8 orders of magnitude off from being able to do this computation. And so often you do need some algorithm design to close that gap, to make something that's feasible that currently was not feasible before, specifically when it's this huge order of magnitude. The other cool thing, though, is that as hardware designers and architects, we can actually influence the algorithm design itself. You need to inform them, not just reducing the number of ops, but what are the hardware capabilities that we actually have? We're really great at parallelism. We're really great at figuring out data reuse and being able to exploit that. So can you add more of that to your algorithm and avoid bottlenecks like memory bottlenecks and so on, because that's more wieldy to handle. And then the other thing that was interesting is that you can use algorithm design to kind of open up opportunities for architects by basically shifting where the bottleneck was, right? So if the bottleneck's purely on like this huge order of magnitude compute, it's really hard to address that from a hardware side. But if you can shift it, and let's say you put it in something like, a little bit of the memory access aspect, and we can address that by banking, then that's great, right? So it's kind of trying to have the algorithm and hardware to work together to really break through and achieve a lot of more efficiency. Okay, so then I'll be brief. This is the last part. So that was, the previous was co-design, how to change the algorithm and the hardware itself. And so now I want to encourage us to think across the entire system. Assuming you did co-design of algorithm and hardware together, basically now we're in a state where we're like, oh, we can do computing very efficiently, okay? So let's say we're in that regime. And so the question is, can we now use the fact that computing is very cheap and efficient to help reduce the other system-wide power that we might face, okay? So let's get into it. So the first example we're going to look at is sensing, right? So again, we want to understand our environment. We already mentioned the fact that we often want to use a depth sensor to figure out how far things are. A typical type of depth sensor would be based on this time of flight principle, where you basically emit a laser, wait for it to hit something, and then it comes back. And based on how long it takes to come back, you can see if an object is very far away or very close. You can, of course, imagine that this is also very power expensive because you're emitting the laser. And of course, the further away the object is, the stronger the laser has to be. So for example, if you want to reach something that's 8 meters, you might have to do 20 watts, and then further it's going to be higher power consumption. In contrast, if you just use like a passive sensor, like RGB image sensor, it's actually going to be much lower power on the order of a couple hundred milliwatts. And so there's a question of, can we, often in these systems you have both the depth sensor and the passive sensor. Can we leverage the fact that the image sensor is cheap, low cost, and reduce the power consumption of the depth sensor itself? So one strategy is pretty simple. So the idea here is as follows. Let's say you have a camera that's a robot that's kind of moving around with these two sensors going on. Maybe what you do is you reduce the on time of the depth sensor. So let's say at time 0, both the depth sensor and the image sensor is on, and then you turn off the depth sensor in time 1 and time 2, but you keep the image sensor on. And the reason you keep the image sensor on is that you can figure out kind of the correlation or how, let's say, this object moves, across the image sensor, and then you can estimate what the depth map should look like from the regular RGB image. And of course, the challenge here is to make sure the cost of figuring out these correspondences in the image domain, or regular domain, is also still low cost. It's not exceeding the depth sensor power, but of course, we know how to do compute cheaply, so you can actually run these correspondences in real time on a very low power CPU. And just to give you a feeling in terms of how it looks like, so this is the regular RGB image. This is, in the middle, is the depth map ground truth, if you actually measured that with the depth sensor. And then the right-hand side is kind of the estimate based on, as I mentioned, the correlation across the different RGB images. So if you just measure it in terms of an objective metric, it's like a 0.7% error. And then here in this particular example, we're only having the laser or the depth sensor on 11% of the time. Okay, so it's almost a 10x reduction in terms of your depth sensor power. Okay, but it's still kind of annoying to still have the depth sensor on, especially if you're not using it that often. So in the robotic space, another challenge is like, okay, let's completely get rid of the depth sensor, and let's bring back our favorite tool using DNNs, right? So what they have is a whole field of research there looking at monocular depth estimation. What does that actually mean? Again, you get this RGB image, and then with this RGB image, with a DNN, can you predict the depth of each of the pixels within the image itself, right? So you can imagine they train this with pairs of RGBD images, and then they get rid of the D. So this is, again, something that's like a very active field in the robotics space. In some of our prior work, we looked at, of course, the task of doing something like this is much more complicated than image classification, which was widely used then. But can we still simplify and use algorithmic approaches to basically simplify the algorithm to do these monocular depth estimations in a very lightweight way? So we applied, a variety of different techniques, and indeed, for the same accuracy, you can get a 10x speed up. And then we were able to deploy it on a phone and show that you can run this in real time. This is at the ICRA conference back in 2019. So giving a live feed of these images, you can do real-time depth sensing of the people itself. This sounds great, but there's still one challenge, which always happens with these neural networks, is that if you remember, in the robotics space, when you're applying the DNN, and I encourage you guys to think about these things rather than just looking at the data set, when you apply it, it's really important that you have a noise model, right? We saw in the robotics space, you need to know what is the noise of your sensor, because that factors into your decision making. How noisy is this data I'm collecting? And of course, DNNs do not have a good noise model, and so it makes it difficult to actually use it in some of these systems without figuring out a way to compute the noise model. And so what can you actually do? Well, okay, if you have an RGBD, you have a DNN prediction. In theory, if you had the ground truth, you would know that this upper left-hand corner has error. but you actually don't have that information, what you would like is some kind of noise model to tell you, hey, this upper left-hand corner, at least be uncertain about it. I'm not sure about it. And like, it kind of makes sense that there's an error because there's a photo there and it's hard to figure out the depth of a painting. But what you would like is some metric that would say, hey, like there's some uncertainty here. I'm not sure about this depth measurement. You know, don't trust this, or like go sense it again, or don't go into this region. You want that information as opposed to, you know, it confidently telling you what the depth is. And the strategy that they use in the robotics community to address this is to actually run multiple DNNs on the same input, as though DNNs are not expensive enough already. So if the idea is that if I run multiple DNNs on it, if there's agreement, then it's certain. If there's disagreement, then it's uncertain. That's the strategy that they take, very computationally complex. And so, as I mentioned, so if you think about this, though, in the context of video, it's running basically multiple DNNs for each frame. But we know something about video, that there's going to be some temporal correspondences between locations in each of these frames. So if you could, again, figure out the temporal correspondences, what you could do is you can have one DNN look at each of the different frames, and as long as you can find the correspondence, like this globe in the upper left-hand corner appears in each of the frames, so you can collect the DNN results for that globe, assemble it together, and then make a decision of uncertainty. If they agree, great. If they don't, it's uncertain. And so as a result, you're only running one inference per frame. And so we call this, you know, uncertainty from motion, and it's inspired by the structure from motion work. Okay, again, this is a lot of stuff. What is the high-level takeaway? I want you to think about expanding the design space to not just be computing, but how can you, allocate energy. In this case, across computing sensing, and then in the robotic space, we had some work also with actuation. But the really exciting thing is that if you're able to enable efficient computing, you can reduce energy consumption not just for the computing side of things, but also for the rest of the system. So you can magnify the savings beyond compute. Okay. So what are the final takeaways of expanding the expanding the design space for co-design that I hope benefits you architects? So I think, again, using modeling to bridge architects with other research communities would be great. You're very good at modeling. We can use this to expand the reach and work with other people. You can use algorithm designs to kind of shift the bottleneck and open up new opportunities for the computer architects to really make an impact in the space. And finally, you can, through co-design, we already showed that you can extend the impact of this research beyond just the computing part of the system. So, my kind of call to action would be, do you want to collaborate, co-design, and get out of your comfort zone? Thank you. That concludes my talk. I should thank all these people.
Mark Hill, Wisconsin, and recently industry. Excellent talk. So clearly the co-design across all those levels is absolutely fantastic for a nimble research project. What are your thoughts about moving it to industry, which has legacy design tools?
Yeah, I agree that that's a challenge. So I would say that first we should show from a research perspective that it is promising and has an impact, and hopefully that could motivate folks in industry to, pursue it, because if it can open, let's say, a new product line or whatnot, it gives them a competitive advantage, then folks might be more willing to figure out how to deal with all this legacy. There needs to be a financial or incentive to actually do it. And so as researchers, we can reveal that there is some benefit, and then I don't know the logistics of dealing with all the legacy kind of stuff, but I think we need to give evidence first that it's worthwhile to pursue, and it's feasible. Right. Thanks, Mark.
Hi. Excellent talk, Vivienne. Jose Cano, University of Glasgow. So in the view that you show us, right, so you cover from the hardware up to the system itself, right? So I think, based on my own experience, one missing part is the software layer, right? And the software layer is quite wide, so we can have there, for example, DNN frameworks, compilers, code generators. I think that, for example, when you want to deploy a DNN model on a device, on an edge device, for example, the choice of the framework you choose, right, can also affect how this co-design, how this design space exploration is done. You talk a lot about robotics, for example. I worked in robotics a few years ago, and for example, ROS, which is the robot operating system, is quite tedious to work with, so implementing SLAM algorithms or other types of algorithms is really tedious sometimes. So what is your vision on that, how this software layer affects this whole stack co-design?
Yeah, so certainly I think the infrastructure to do end-to-end design is not there. I would say my students, they use ROS when they need to do a demo with the system, but like, for example, like the GMM map work and the FSMI work were all outside of the ROS framework itself, so they just avoided that whole infrastructure just to demonstrate it's feasible. Once it's actually feasible and it's promising, then they'll deal with that wieldy framework. So once again, it's more, I think, generally the way I like to frame our research is first we want to show what's feasible, and then we do the engineering work, whether it be engineering work to tape out a chip or to do a system demo afterwards. But we first to show that's meaningful to do. But yes, there's a lot of engineering effort that's very clunky at that back end, and maybe there will be, as we show that this is a more promising approach, there'll be more efforts to make that less clunky. That's the whole.
Okay, thank you.
Yeah.
Okay. I am Sarita Adve from Illinois. Thanks, Vivienne, for super high bandwidth, very high signal talks. Really appreciated it. So my question is, I've noticed in your work, you do a lot of specialized accelerator design, right? Which is great. I buy the whole co-design stuff and so on. But in this field, like robotics for you, AR, VR for me, which are very common, lots of commonalities, the algorithms are moving so rapidly that how do we justify building hardware accelerators that are so specialized to solve these problems? And picking up from your talk, let's say Gaussian representation for scenes, right? It's just like the craze now, but it's relatively recent, and I think most people believe that new scene representations are going to show up. So, yeah.
Yeah, great question. Thanks, Rita. I think there's two ways to approach this. So one is, again, trying to figure out, would you get significant savings if you were to do, let's say, Gaussian representations and co-design the hardware? So what is the potential of what you can achieve there? I think only once you establish that, then there's the question of, well, how much flexibility you do actually want to introduce into the system to support a wide range of things. I think there's, you can come from the other end, which is that I can get a range of workloads. I need to figure out what those workloads could be and then design an accelerator for that with a lot of flexibility there. Or it could be, I'm going to change the workload as much as possible to minimize the energy consumption along with the hardware and push the limits. I think these are two, they'll meet in the future, but I think these are two different strategies. We've taken the second one, which is just really trying to push, basically try to show that with co-design you can make what's impossible possible. But of course, I think from a product standpoint, or to last in the future, you need to have some flexibility. And the question is if this is a direction that we want to go into, then how can we ensure that there's flexibility with other types of workloads as well? So that's been the strategy that we took. That being said, in my prior work for video compression, when things are standardized, then you really push specialization, and that's why we can all do HD video on our phone. So there is a role for very highly specialized. Again, it would be the trade-off between how sensitive are you to compute energy? But I completely agree. I think looking at a flexible, the trade-off between flexibility and efficiency is really important to support a wide range of workloads. And we heard from the sustainability panel too, you'd love to have this hardware last longer and not just have to be replaced all the time.
Thank you.
Try to answer the second question, which is, can we even make it possible to do certain things? Thanks, Rita.
Ben Feinberg, Sandia National Labs. During your compute and memory section, you talked a lot about energy efficiency, and then you also mentioned the word analog. Can we do accuracy with analog, or is it just efficiency for a worse solution quality?
Oh, you mean analog computing and how? I think this is a big ongoing question. There's a lot of research in the space about whether or not how can you handle the analog, the noise that comes with analog computing. There have been some strategies that are you do some local tuning of the neural network to fit this noise for a given platform, but that's a little bit infeasible from a cost point of view. We did some work looking at, how robust certain neural networks are to noise. So this was another part of that rethinking DNN design. So it turns out a lot of these neural networks that are, giving you very high accuracy on digital processors are actually very fragile when it comes to noise, and so the accuracy plummets on these analog processors. So the robustness of the DNN to noise, I think there's a lot of research in that avenue as well. But I think it's still to be seen whether or not, this is actually a solution that you want to pursue because you have to deal with a lot of the analog noise, which, analog computing has been around for a long time, and the noise has always been something that is a challenge. But I think there's, if you can show that there's, again, enough energy gain from doing this, then it motivates people to try and solve this accuracy challenge. But yeah, it's not clear to me which is the winner, and I hope that, with a lot more kind of co-design across the stack, we can actually push both and see if it's feasible, if it's worthwhile to do.
Thank you.
Sure.
Thank you.
Okay. Thanks, everyone.
Thank you, Vivienne. That was an inspiring talk. So just a couple of announcements for the presenters. Please come up to the front of the room and meet the session chair and make sure you introduce yourself and make sure that things are all set. So we're going to get rolling into the next session. Thanks again, Vivienne, for that inspiring talk.